Okay, so today we have this problem where we want to translate this signal into the frequency domain. Right now it's in the time domain, and we want to go to the S domain or the frequency domain. So let me write it down. So it's the time, this is frequency. So we are trying to find the Laplace transform of this signal right here. And so that's what we are going to do. And right here, what we have is a unit step function or unit step signal plotted here. And we are trying to switch over to the frequency domain. So now let me go ahead and break this problem down for you. So right off the bat, right, we can go ahead and tell that this right here, it's in the time domain as stated there. And so if you have any previous knowledge of signals and systems, or just signals in particular, right, in general, I guess I should say, sorry, you could tell that we have a time delay. We have a time delay, which meaning, right, that we can go ahead and write this function. We can go ahead and write this as u of t minus 2 minus u of t minus 4. And that's what we have, right? That's in the most basic form, right? What we have in plotted up there. I can actually go ahead and make a video on how to plot this on MATLAB, which I will. I'll go ahead and post that as a follow-up. But we have a unit step, right? If you don't know what the unit step is, if you have any knowledge of differential equations, the unit step is just pretty much the same as the heaviside function, h of t. It's just a step function. Very useful. So now that we have obtained this, we can go ahead and plot this, and that's what I'm going to go ahead and do. That way, just for demonstration purposes. So let me go ahead and do that for you. So we have, and let me just go ahead and actually go through the full motion of things here. So what we have, and let me switch colors. So what we have is pretty much a signal coming all the way from negative infinity, coming up, right? Because the unit step function is defined as 1 for t greater than or equal to 0, and 0 for t less than 0. So yes, because it's 1 for t greater than or equal to 0, or t or 0 for t less than 0, right? So here what we have is that we have 1, right? And so what we have here, this is just a unit step. Literally, it'll be going to infinity right when it hits 1, right when the t hits 0. I can go into a whole definition of why this is, right? But for right now, just trust me on this. I mean, I can post. This is just assuming, right, that you have some sort of knowledge on signals. So what we have here, though, is that we have u of t minus 2. So let me go ahead and work on that. So what we have is this right here. So it hits 2, and then over here we have that it hits 4. So in that regards, for u of t minus 4, actually, so what we have here is this, and let me switch colors. And for u of t minus 4, what we have is this. Let's see. That's what we have. The main reasoning why we have why this is flipped upside down is because of this right here. We have this minus. Minus means that it's flipped, and so that's the main reason why u of t minus 4 is flipped. Once we combine those two signals, though, we will get the above, which is this right. Okay, so now in regards to solving this problem right here, this main problem and trying to figure out the Laplace transform of this signal, we have to just focus on this part right here, which is the u of t minus 2 minus u of t minus 4. This right here is what we're focused on, and we want to go ahead and go from this time domain into the S domain or frequency domain. That's our main interest. So in regards to that, you can, if you wanted to, you could just go ahead and forget about all these visuals and stuff and just go ahead and focus on solving for it, but there would be no reasoning behind it, just because of the fact that you would just be going through the math and you would not be able to see what you're doing. So I really wouldn't recommend that. But let's get to the point. Let's go ahead and take the Laplace transform of this function down here for this problem. So let me go ahead and go down. And so let's go ahead and formally write this. And we are interested on taking the Laplace transform of this. Now, as we can recall, or if this is new to you, I recommend looking at the Laplace transform table. But in case that you're familiar with this, we know that the Laplace transform of a unit step function or a heaviside function is actually equal to 1 over s. You should know that by heart if you're studying this stuff. That's 1 over s. However, we have a special case for this type of heaviside function whenever it's just not u of t by itself, and instead we have a minus, like in this case, like we have a u of t minus 2. We have a special case for that, right? And let me go ahead and write down the formal definition for that. So let's say we have some value that's c that's greater than 0. So if that's the case, by this definition, we should be able to take the Laplace of that and write this down as u of t minus c. That's if c is greater than 0. So in this case, we can go ahead and write this like this, and we are allowed. So the Laplace transform of this in this case would be e to the negative cs over s, and this is the formal definition for this problem, because in this case we have u of t minus 2. Now, don't get confused, right? Because this says c has to be greater than 0. It would be different. In this case, in our problem, c is greater than 0 because we have 2. Because think about it. If we were to have u of t minus negative 2, now this will not be greater than 0. Therefore, this would make this problem false, right? So that's just something to keep in mind. So in this case, our problem does fit the definition. Hence, we can apply this property to our problem. So with that being said, sorry about that. So with that being said, we can go ahead and write this, or our answer. Go ahead and write this as e exponential to the negative 2s over s. Oops, I'm sorry about this. I'm barely noticing this. Minus e to the negative 4s over s. And this right here will be our final answer. And this right here is the Laplace transform of this given signal. And that should check it. Thank you.